Hello everyone, I'm Karthik from ITA section. Today I'm going to discuss about autonomous quadrator for accurate positioning. In embedded systems, this is my topic. Let's dive into our topic. Coming to the introductions, embedded systems are everywhere and they present unique challenges in verification and testing. The real-time nature of many embedded systems produces complex failure modes that are especially hard to detect and prevent. To prevent system failures, we need to understand the nature and the common system of software anomalies. We also need to think about how mistakes lead to observability anomalies and how this can be differentiated according to their reproducibility. Another key need for efficient fault detection is comprehensive observability of a system. This kind of understanding leads to principle of scientific debugging. Mistakes, errors, and defects, bugs, faults, and anomalies. In everyday language, we use a number of words such as bug, fault, error, etc. inconsistently and confusingly to describe the malfunctioning of a software-based system. This also happens to the authors of these papers in their normal life unless they pay strict attention to their choice of words. Therefore, we would like to start with a brief clarification based on the terminology used by the IEEE standard classification for software anomaly. If coders notice a mistake themselves, it is called an error, a human action that produces an incorrect result. If the tester is the first to notice an anomaly, a product does not meet its requirements, it is called a defect. After confirmation by the developer, it becomes a bug. If an end user finds the problem manifestation of an error, we have a fault, that is IEs. So figure 1 illustrates the semantics of anomalies. The term anomaly may be used to refer to errors, defects, bugs, as well as the faults. So it refers to something that deviates from what is expected or normal with respect to the required behavior ideally defined by system specification. So here the figure 1 is the semantics of mistakes, errors, defects and bugs of faults and anomalies. So here mistake is misunderstanding and it leads to the deviation from the expected behavior identified by the developer or tester or the customer, which are the roles, and the developer finds the or identify the error, it is called as an error, or the tester identifies it, it is called as an defect, or customer identifies it, it is called as a fault. So this is accepted by the developer, that is called as a bug. Reproducibility of the anomalies. The underlying causes for an anomaly are so complex and obscure that it appears to be the non-deterministic. We speak of an Mandel bug, named after the chaotic Mandelbrot set. Race conditions seen in concurrent programs are common examples of Mandelbugs. The literature defines subclasses of the Mandelbugs. Aging-related bugs occur in long-running systems due to the error conditions caused by the accumulation of the problems, such as mirror leakage, propagating rounding errors, or unreleased files and logs. A typical example for an aging-related bug is the software fault in the Patriot missile or defense system. Anomalies that seem to disappear or alter their behavior when looked into are called Hans bugs, named after the uncertainty principle described by the physicist Werner Hansberg, which is often informally conflated with the probe effect. It might seem that the predominant class of faults should be complex Mandel bugs. This is not the case. In the practice, there is surprisingly high propagation of Bohr bugs. An example is given by the Grotte, who analyzed the software faults for 18 JPL NASA space missions out of 520 software faults. 61.4% were clearly identified as Bohr bugs and the 36.5% as the Mandel bugs, 4.4% of which are aging related. Patriot's fatal law. On February 25, 1991, during the first Gulf War, a Patriot air defense system near Dhahran, Saudi Arabia failed in its task of defecting and intercepting an Iraqi Scud missile. The result was that it hit American barracks unhindered, killing 28 soldiers and injuring about 100. The reason was an aging-related bug in the weapon control computer, an inaccuracy caused by the rounding. A floating point variably continued to propagate. With increasing operating time, the target detection became so inaccurate that the trajectory of attacking missiles was wrongly judged as harmlessly. The anatomy of an anomaly. The possible effects of a mistake are illustrated in the figure 2. Our example system traverses through a sequence of states Z1 to Z6 which are characterized by internal variables I1 to I4. The system produces the observably outputs E1 and E2. Each program execution step computes an update to the internal variables and the outputs to produce. If the executed program contains a mistake, that resulting the state might not be as expected. In this case, we speak of an activated mistake and a resulting infected state where an anomaly has manifested by the transition from state Z1 to Z2. Two code segments with mistakes are executed. One of them computes a wrong state of internal variable I3 and the other code B produces a wrong observable output E2. The latter is a textbook manifestation of a Bohr bug as long as the anomaly can be reproduced under a well-defined but possibly not understood set of conditions. This is a figure a defective program execution as a succession of the states, left hand side and extended depiction of states and transition, and coming to the right hand side compacted depiction of the same scenario. These are the execution steps followed at every step, and the right hand side is the compacted depiction of the same scenario. The debugging process. The process of understanding the underlying cause of an anomaly cause uh, that is that is the identification of the mistake and fixing the problem is called debugging. Starting from an observed anomaly, a hypothesis that narrows the space of possibilities for its cause is developed. The next step is to develop an experiment to test this hypothesis. If the hypothesis is supported, either the detected mistake can be understood and fixed or the hypothesis can be further refined. If the hypothesis was false, a new hypothesis has to be developed. It is obvious that the observability is a crucial factor for an efficient debugging process. The technology and the tools to cope with the complex faults in debugging in embedded systems are now becoming available to the engineers. The figure 3 is the printer for debugging, and at B is the start and stop debugging, and C is the omnistic debugging, and D is the runtime verification, and E is the novel approach combining both best of the omnistic debugger and the runtime verification approaches. This illustration follows the representation introduced in the figure 2. Use case smart sensor for nuclear power applications. The author recently conducted a study on applying software systematic testing process on an embedded smart sensor device representative of the type found in nuclear power generation applications. Nuclear power generation facilities worldwide are steadily trending towards aging infrastructure, with the average age of light water reactor in the United States at about 37 years. The need of modernize this generation facilities with software based INC systems and smart sensor is a high priority for the industry. This system have to be tested and validated to every high level of a system assurance to ensure a reasonably possible that no software faults exist. The systematic testing methodology employed is called a exhaustive testing, which is built around T-way combinatorial testing, partitioning and boundary value analysis, and MCDC path analysis. We applied the systematic testing of a software following the well-known unit test, integration test, and the system test paradigm. A test bed architecture was built using state-of-art test automation tools necessary to conduct the real-time systematic testing and experiments on the smart sensor. Coming to the conclusion, embedded systems are becoming much more commonly in daily life, and better ways of finding and preventing failures are essential. The complexity possessed by cyber physical systems present grand challenges to testing and verification. The state of practice for embedded software is at a point where new methods and novel techniques are needed to adequately test these critical systems. This is about our topic. Thank you.